Say something there.
Hello?
Bill? A little bit more. You can't even beat out a dark room right now, pal.
Hello, hello, hello.
There you go. Now we're good. All right. We just finished 23A. I got to get some stuff going here. What's coming up? Next week, we have to finish all of chapters 25 through 27. Whatever, the rest of the book. Yep, 27. And then on Thursday, we're going to have the review. The test will be on the 17th. Get your assignments done between now and then.
Are we going to have class on the 18th or is it 17th?
18th is after this semester is over. 17th is the last day of the semester.
All right.
Yeah, graduation is the 18th.
Yeah, great breakfast.
Is that you, Rose?
Yes, I was bringing cookies.
Did you bring enough for us? You could send them through the TV for us. We would appreciate that.
Wouldn't that be nice if we had just a box to put it through?
Yeah.
Yeah, Bruce came to visit yesterday the campus, and then he brought a whole tray of cookies, and I thought,
Well, that was nice of him.
Yeah, I thought I'll divide them up between the two rooms, and looks like it's a hit here. So, have a good day.
See ya. Okay. So let's take out our notes, because what we're talking about here is on page 24A, they show a diagram. But before you can understand the diagram, you have to understand where the diagram comes from. So on our notes, let's talk about exponential and step growth. Okay, so say for example, we want to increase by 100% per year, and then the important thing is that we're going to compound. If we don't compound, none of this makes sense. Now, what does compound mean in connection with, say, interest, for example? You make money, not just on what you put into the bank, but on the interest that what you put into the bank earns. Okay? Everybody good with that? So let's look at this first Desmos that I've got for you. Come on. We want to go from x equals negative 0.1 to 1.1. We wanted to go just past the first year. In the x direction, we want to start at negative 0.1, and then let's go up to, say, 3. Now, the reason we need to go to 3, you won't see on this first graph, but you will see it later on. Okay, so let's look at this first graph, and it shows. So if we start at $100 at the end of the year, okay, at the end of the year, we double it. Or if we start at $1 at the end of the year, we double it. We now have $2. Everybody agree with that? So let's draw that first step. So if we have this situation, now here's the compounding problem that we've got. I'm going to draw my axes here. So here's 1 year, here's 3, okay? And I start out at 1 year, $1, I go all the way over to 1, and then I double it. I'm now at over 1 up 2. Everybody agree with that part? Okay, and my formula is $1 times 1 plus doubling, or in other words, 1 plus 1, to the first power. So what this is saying is I start with 100%, and I double it. I add 100% to it, and I do it for 1 year. Think about the math. Does it make sense? 2 to the first is 2. 2 times 1 is 2. Everybody good with that part? Okay. Here's where compounding comes in. Now, I'm going to compound it every half a year. So in other words, I'm going to start at my $1. I'm going to go over to halfway through the year. I'm going to not double it. Why not? Because I'm not going to double it until the whole year is done. So how much do I increase it by the first half of the year? 50%, right? So does it make sense that now I'm at 1.5? Okay? Then I go along till the end of the year, and now I double what I had here. Not double, excuse me. I increase it by another 50%. So let's draw the picture, and then let's do the math to show how that works out. Okay, so here's what's happening. We go along till halfway through the year, and at halfway through the year, we take $1 times 1 plus a half to the first. Why a half? Because over the course of the whole year, we're going to double. So if I go halfway through the year, I only increase by 50%. Then I go the other half of the year, and I increase by the other 50%. So how much do I have here halfway through the year? Halfway through the year, I have 1.5, right? Because I took my 1 times 1 plus a half, 1.5. Got it? Then, at the end of the year, so I go along all the way till the end of the year, and now I do the exact same math again. I take what I had, 1.5, and I multiply it by 1 plus a half. Well, what's 1 plus a half? 1.5. Do it on your calculator, and what do you get for an answer? You're going to take 1.5 times 1.5 is 2.25. So by compounding, right? By compounding, do I have more than I did if I wouldn't have compounded? Yeah, if I wouldn't have compounded, I'd only had 2. Now I've got 2.5, right? Okay? Next, I'm going to compound it every quarter. Okay, so 1/4 of the way through the year, how much percent should I be giving? 25%. Another quarter of the way through the year, another quarter, right? So I've given away 50%. Another quarter of the way through the year, another quarter, so I'm at 75%. And then by the end of the year, so how many times do I compound in that year? 4. So I've got 4 steps here, right? Okay? Now, the math for that could be written as I'll do the math in a table form. So we start with, at time 0, we have 1. Time 0.25, time 0.5, time 0.75, time 1. Okay, so if we increase it by 25%, how much will we have? Oops, I didn't do that right. This is the time, this is the amount. So if we start with 1 and we increase it by 25%, how much do we have at the end of the first quarter? 1.25, right? Now we need our calculators, and we're going to take that 1.25 times 1 plus a quarter, right? And we get 1.5625. Is there another way that you can do that math? Yeah, you take 1 times 1.25 to the, by the time we get down here, how many quarters will we have done? 4, right? So 1 times 1.25 to the 4th is 2.44, 1, blah, blah, blah. Now, if you notice, I didn't fill in this spot right here, right? I could have. What would have I done? I would have taken 1 times 1.25 to the... I would have taken 1.5625 times 1.25, right? I just keep multiplying by 1.25. So if I take it times 1.25 times 1.25 times 1.25 times 1.25, I get my answer. I'll show you that with this problem here. So I take 1 times 1.25, and I get 1.25, times 1.25, and I get 1.5625. Times 1.25, and I get 1.953. If I do it one more time, what do you know the answer is going to be? 2.44. So times 1.25, and I get 2.44. So let's go back to Desmos, and let's see what happened here. So if you look over here, when we compounded it just once a year, the green line, we got 2. When we compounded it every half a year, we got 1, I forgot what it was, 2.25. When we compounded every quarter, we got 2.44. What seems to be happening the more times we compound? At the end of the year, we end up with more money, right? Okay. Will that keep on happening forever? Well, let's do the next one. Now, the next one I don't do 8 because that's not a common way to do it. I do 12. Why do you think I compound 12 times?
At least for my savings account, it's at the end of every month.
Sure, it's monthly. So here is 1 month, 2 months, 3, and so on. Do you notice what the orange line has compared to the red line? at the end, it has a still higher amount, right? Okay? Well, how would we do that? Mathematically, here's what we would do. We would take parentheses 1 plus 1/12, close parentheses, to the good. And we get 2.613035. Okay? Now, we can do daily, if we doubled it, so that at the end of the year we would have doubled it daily. In other words, each day's interest would be 1/365th, right? 2 365ths, 3 365ths. But what would we raise our power to? To the, how many times would we compound in that year? 365. So let's do the math for that. 1 plus 1 divided by 365 to the 365. And we get, so I'm going to, on my table here, do monthly, T and amount. 0, we had 1. By the end of 12 months, we had 2.61. Okay? Now I'm going to do daily. This is monthly. Now I'm going to do daily. So I would start with, on day 0, I would start with 1. And by the time I had done 365 times, I would get 2.714 and so on. So on my graph, so here's my graph for half. Then I could do a graph for a quarter. And what's interesting about the graph for a quarter is that by the time you get to halfway through, you're a little bit above where you would have been on the previous step. And then you do another quarter, and by the time you get to the end, of course, you are a little bit above, where you would have been there. Okay, then you do monthly, I'm sorry. So by here, you would have had 3 steps, you'll be a little bit above. Then you'll have another 3 steps, be a little bit above. Now, you get the picture, right? It's going to, I did not draw my steps very good. But you see what's happening. As you compound more often, and then you get to 365, well, by the time you get to 365, these steps right? Those steps are so small that if you look at them from where you're sitting, it looks almost like a line, right? Oh, we wouldn't say a line, a curve, right? Because we can tell it's not straight. Okay, if anybody wants to help me out by making the table here, that would go with daily. You can see my monthly table is this big. Okay, my daily table will be huge. I don't want to do it. But if you want to, where would we end up on daily? We just did it. What number did we end up with for daily? 2.71. Now, can we compound more often than daily? Sure, we could compound every hour. Then we could compound every minute. Then we could compound every second. Okay? Could we compound more often than that? Is there a time shorter than a second? Yeah. The word that we're looking for starts with in and ends with staneous. Instantaneous. I didn't say that right. The word I said was instantaneous. That's not the word, Kevin. Instantaneous. Okay? How do we do instantaneous? Well, interestingly enough, there is a number that allows us to do instantaneous on here, and that number is E. Oops, you can't see that graph. That number is E. What's the difference between that and the black line that I made? Well, this one has steps, right? The purple line will have no steps at all. It'll just be there, okay? Now, why is that significant? Let's give some examples. Horse, fish. Oops, I better do fish in a different color. People, germs. So we are going to graph population of horses, fish, people, and germs. Anybody in ag major that would be able to help us out with horses? Anybody know anything about horses? Kind of. What do you know?
Some stuff.
Okay, but we're talking about their population.
Oh. Yeah, no, I don't know that.
You don't know that one. Horses have foals in the spring. Okay? The babies are born sometime between the 1st of January and the 1st of March. Okay? For horse racing purposes, every horse is born on January 1st. Okay, so you want to make sure your horse is born after January 1st, but before like May, because you don't want them to be like the young kid out there racing around the racetrack with the rest of the 3-year-olds or 2-year-olds. Everybody good with that? Okay? So you have to plan ahead, right? You have to make sure the mare gets inseminated sometime in the previous, I think their gestation period is about 11 months. Check it out, internet people. I think that's about right. It's 12. Okay, so basically that mare is either always pregnant or she's always got a foal. One of the two things is always happening. These kids, they never leave me. Okay, it kind of reminds me of the deer in our backyards. 3 years ago, she had one foal and one doe. Okay, and that guy followed her around. He's kind of sometimes around, sometimes not. He's got some antlers. Okay, 2 years ago she had twins, and so they're still following her around. And then last year she had twins again. So she's got like these 5 kids that are always following her around. Now I have no idea who the father is, okay? Now, I do have a picture of this guy that's got one antler going out like, oops, where am I? Oh, I see. I didn't put my picture right. Of one guy that he's got one antler going this way and the rest of them are up like this. I don't know. He looks a little sketchy. Maybe he's the dad, maybe he's not. I don't know. I don't judge. Okay. Horses, fish, people, germs. So let's graph the population of horses. Here's year 1, year 2, year 3. Okay, so let's start with a certain number of horses here at time 0. Okay, so sometime between that first day of the year and about March, the horse population increases. Everybody agree? Does it double? That's a good question. Probably not, right? Because most horses just have a single foal at a time, right? And there's always one guy involved, right? And at least one, okay? If we're talking about wild horses, I don't know what they're... But then what happens the rest of the year? Well, the rest of the year, the population slowly declines. Not by very much, probably, until you get to the end of that first year. Then what happens? Population goes up till about May, and then it gradually declines over the course of time till the end of that second year. And then the foals are born, and they gradually, I don't know, maybe horses get old and die or whatever. But you see how horses have a very step-like nature. If you were going to graph population of fish, I chose them on purpose. We're talking just about number. Okay, I'll do it. First of the year. Let's take like bass as an example, because if we were talking about, say, tullabies, they breed in the fall. Rainbow shiners breed in the fall. But let's take bass, and I'm going to put bass way down here on the first of the year, and that goes along, say, until about May. In May, the population goes up, say, 10,000 times. Now, I don't know if that's an exaggeration or not. You could check it on the internet to see how many eggs a female bass lays. But 10,000, I don't think, is insurmountable, right? Okay, so she has 10,000 eggs. But almost immediately, they have a very steep exponential decline in population. How steep? Well, so that by the 1st of July, there's maybe 10 times as many left. What happened to the rest of them? You didn't know this about bass? They eat their young. Okay? So your mama would just say, you know what? I love Maddie, but I love how she tastes better. Okay? Just eat her. Okay, so the population just declines like crazy. And then by the end of the second year, there might be some more fish. I don't know. But then the same thing happens again. It's going to increase by 10,000 times and then decrease exponentially. So you've got this population. If you were graphing population over the course of time, none of these models that we're talking about would work very well. Let's talk about people. Why does the population of people increase like this? Raise your hand if you were born in January. Raise your hand if you were born in February. Raise your hand if you were born in March. Raise your hand if you were born in April. Raise your hand if you were born in May, June, July, August. Did you raise your hand twice? September. No, I'm just kidding. I was just giving you a hard time. September, October. November. December? Did I miss somebody? Oh, okay. I was wondering. I was like, wow. So we have a bunch of December. Does that mean that most people are born in December? No. Would you agree the population of people, people just are born at any time through the year, and the population is going to increase like that. Now, that is if people, population is exponential. Here's what's happening in the United States. Here is 2014. The population of the United States has been growing linearly since about 1955, right around there. Why did I stop at 2014? It's just in today's paper. Oh, maybe it was Time Magazine. No, it was today's paper.
Did we hit 1 billion? Or one of the billions, didn't we?
Oh, okay.
haven't we have a negative population though?
Since 2014, in the United States, the life expectancy has gone down, which has resulted in a flat population according to breeding. Why does the population of the United States keep on growing? We keep on getting immigrants into our country. And so it changes things. Now, there are some countries in the world that have population decline. Italy went like this and then back down. Italy has been declining in population for about the last 40 years. Why? Each family, instead of having 2, 3, 4, 5, 6 kids, maybe one, and maybe some of them don't even form families. They just like, whatever, I don't like kids. Well, I like how they taste, apparently, but I don't. No, that's fish, that's right. Now, here's where exponential growth always works, and that is with germs. Okay? Why? Well, because like most germs reproduce like crazy. Maybe doubling every day, 2 days, 3, I don't know what their doubling time is, but it's very, very, very short. They just increase like crazy, which causes people to get sick, right? Because the germs grow faster than the body's ability to kill those germs. Page 319. So, here is a graph. The curved line is a graph of some value A to the x. The straight line is a graph of a line x plus 1. Question 1. What is the intercept of that line? What is this point right here? Coordinates of this point right here. 0, 1, right? Why? Because the intercept is 1, and what's the slope? M equals 1, right? So if you go over 1, you'll be up 2. If you go over 2, you'll be up 3. If you go over 4, you'll be up 5. If you go over 10, you'll be up 11, right? Everybody agree? That's the slope of that line. Here's what they're saying. In this kind of a function that we've got here, we're taking 1 plus, remember how we were doing? 1 plus 1 over infinity to the infinity. So in other words, that denominator gets bigger and bigger and bigger and bigger. Well, at infinity, it will be 0. Any number to the first power is 1. So at infinity, it will be 1. But we're not talking about that. What we're talking about is what happens as this number gets bigger, but this number also gets bigger. Where do we end up? Okay? Well, let's look back at the graph. On this graph, where did we end up with E? E to the first. Let's press it on our calculator and let's see where we get. So on, clear, E to the first. We end up at 2.71828. So what we're saying is, for these germs, which reproduce an infinite number of times per year, you would have to take that to the infinite power. This part right here, where you have two things like that, that ends out to be the number E. Why is that powerful? Well, we think, if this is infinity, I have one pizza and I divide it by an infinite number of people, each person would get no pizza, right? But I take it an infinite number of times and I get to the number 2.718. I get to E. Page 318. I think, or 319. I think we now have enough information to go through this assignment. Let's see what happens here on this assignment. Where'd it go? 24A. So I've got two things going here. Oh, I gotta start over again. I'm gonna start at my x-axis going from negative 10 to 10. My y-axis going from negative 10 to 10. Okay, so there are my two curves that we're talking about on page 320 or 319. Now, I'm going to change this A value so that you can see it. See it how. Come on. See it how they want it to be. Okay, so they're showing it where there's an obvious gap between these 2 points. This point here and the point where the two graphs cross each other. So I'm going to show those 2 points of intersection. Obviously, one of them has the address 0, 1. The other one has this address up here. So, the first question that they ask is, what happens to those two lines if you take A and you make it bigger? Let's make a table here of values, and that might help us. Okay, so if we have values for A and A to B. So I'll just do the line A to B. So if we take A is 1, well, here's a graph where A is 1. It doesn't surprise you that it goes straight across. I'm going to take 1 to the first, 1 to the second, 1 to the third, 1 to the fourth. Okay. The distance between A and B is 0 because they don't cross each other, right? But we want to make it bigger than that. So let's go to 1.5. So if we take 1.5, now from A to B goes from over 0 up 1 to over 3.93 up 4.939. Okay, so let's graph that. So our curve goes from this point to this point, 3.93, 4.93. Okay, so here is our line connecting them, and here is the curve connecting them, and that's because we have 1.5 to the x. Right? Because we said our base, A, is 1.5. Does it make sense that we would go through the point 3.93, 4.93? Does it make sense that these two numbers are one apart? Yeah, because our line, remember we said, if we go over 3, we go up 4. We always go one more up, then we go over, right? Everybody good with that? Well, let's look at the addresses of some other points. Does it make sense that when we're here at 1, if we go over 1, we would be up 1.5? Yeah. If we go over 2, does it make sense we would be up 2.25? Yeah, because 1.5 to the second is 2.25. If we go over 3, does it make sense we would be up 3.375, right? And then if we go over 5, well, let's press it on our calculator and let's see what we get for an answer. If we go over 5, so 1.5 to the 5th, 7.59. Okay, everybody good with that? Suppose the value of A increases, what happens to the points A and B? So now let's go to 2. Do you notice, I'm going to click on the curve to show you that these 2 points, what happened to the place where the curve met the line? Those 2 points got closer together, right? So if A equals 2, that distance was from 0, 1 to over 1 up 2, right? So our line changed so that this line here got to be these 2 points much closer together. Over 1 up 2. This was over 0 up 1. So those 2 lines are getting, or those 2 points are getting closer and closer together. If we try 3, and we look here, do you see what happened to our points of intersection? If we tried 3. It's negative, right? So at some point here, so let's draw the graph of 3 just so that we can see what happened here. Here's our line. And now, instead of our point being in front of, our point that we cross is behind. So in other words, this point that used to be the trail point is now farther to the right instead of farther to the left. So this is what happens when you have 3. You go through over 0 up 1, that's for sure, but you go through negative something up something smaller than 1. So what they're asking is this. In preview 24A, you learned that a line is tangent to a smooth curve at a point if the line intersects the curve at P without crossing the curve at P. We will see how the tangent line can be useful in approximating more complicated functions. Page 320. The following graph shows f of x equals x plus 1, g of x equals a to the x. They want us to graph this so that a is the interval from here to here, and our window goes -2 to 2 and -1 to 3. So I'm going to change my window. I got this way too big. Okay, so I'm going to change my window so I go from, x goes from -2 to +2. Y goes from 3. 1 to 3. Okay. It says what happens if you change A so that it goes somewhere between 1 and 4. Let's just watch what happens as we go from 1 to 4 on that interval. What do you see happening to the place where the graph intersects? Tell you what, I've got one more thing I'm going to do here that will help you. Pause. I'm going to add a point that will help you. And the point is going to have the address A, comma, A to the X. Oops. No, we have to do F. Oops. Let's go up here. Forgot what we called that function. G of B. Okay, and that's going to be a E, comma, E of G. Let's play it again and see what happens. Oops, that's not the one we want to play. Okay, so yes. What am I doing wrong? Why is it going straight up and down? Over. Let's see. B, comma. Let's take F of B. No, that won't do it either. I'm trying to get where those two intersect, and I can't. Can't I graph A, comma, F of A? There we go. Nope, can't do it that way either. I'm trying to show you where these two lines cross, and I can't get it to show up right now. But if you notice here, it fluctuates between being above it and being below it. So let's try to get it so that our point of intersection is really, really, really close to 1 here. So I have to go a little bit bigger than 2.1, 2.3. So you see how that point is getting closer and closer and closer. I'm going to stop right there for just a second. And then I'm going to go to page 320, number 3. Now change the viewing window so that you go on the x-axis from -0.001 to +0.001. And the y-axis, you go from 0.999 to 1.001. So we're really, really close here with these two, but if you notice, let's get the two curves. I can't get them both to appear, can I? It won't show me both of them. It'll show me the one where they cross, but it won't show me the other one. So as you zoom in, those two lines get closer and closer together. If you keep on zooming in, what's the next one that they say? Eventually you will see that if you keep zooming in, the blue line and the green line, if I keep zooming in, and this value gets closer and closer to E, 2.71, those two lines get closer and closer to each other. So, on our notes, we would do it this way. If we zoom in, so that we go from, say, 1.1, 0.9, we're going to cross between those two, but our green line, the curve, and our red line, the straight line, are going to essentially be the exact same value. Number 4, mathematicians denote the letter E for the exact value for which the graph y equals x plus 1 is tangent to the curve y equals e to the x. Most graphing calculators and apps can approximate a constant value of e, and we got that 2.71. What does that mean? Well, how do we use it? It says scaling the input of a function stretches or shrinks the graph horizontally without changing the vertical intercept. So if we scale the input, while this stretches out, it doesn't change where we cross the axis. Page 321. Use that fact for this problem. Based on experimental data, a biologist estimates that for a small values of time, the size of a bacterial colony, L of t, is 0.034 t plus 1, where t is the time measured in minutes. However, the biologist knows that the bacterial colony grows exponentially. So we can say t plus 1, which we know has to be equal to e to the t. The only way that's going to work is if we multiply this by 0.034, which means this also has to be multiplied by 0.034. Check your graph, it says. So in E3 or in Desmos, we would graph 0.034x e to the 0.034 times x, and I got to turn off those other marks. So if you notice, those two functions are the exact same. Oh, I put the 0.034 in the wrong spot, didn't I? 0.034. So if the linear function grows by 0.034, the exponential function grows by 0.034 also. How could you estimate the value of p of 10 without using your calculator? In calculus, we make a big deal out of linear approximations of exponential functions. Don't know why, but we do. And what they're saying is this: if you can get it down where you have a percent, and that percent is small enough, it will be essentially the same as the exponential function to that power. How would we do the math? Well, yeah, it comes out to 0.0346, something like that. Linear approximations of exponential functions is what they're showing in this picture right here. When we come back, we're going to do some more work with compound interest, section 24B. Menominee, can you talk? Because all I see is dark room there over in Chippewa.
Hello.
Hey, thank you.
So on the homework for 12B, it had a -3 rate of change being more than a 1/3, -1/3.
Okay, so 24B,
12B,
assignment 12B.
yes.
Okay, let's look and see.
I need to have like job ends.
Is it okay if other people see what your grade here? Because otherwise
Yeah.
Why do you need to Sharpie it? Because just don't question the OCD. Just I can't explain it. Just scribble it.
Do you remember which question it was?
I do not.
No, you said -3.17. Calculate the average rate of change of stress of the intervals defined by the points in the table for the function p or rho of a. So you take. So what you would do for this first one is take 150,000 divided by 200. Away from 150,000 divided by 300, and then divide that thing by 100.
Yeah.
So you knew what you did wrong there.
Yeah.
Okay. So this isn't the question you were talking about?
No, it's just the rate of change. Like I think farther down one of the next questions. Okay, so as the area increases, the rate of change of the stress decreases.
You said then increases.
Yeah, but can you go up and look at the table?
I paint those. No.
Maybe that's the values that you got.
So as the area is increasing, the numbers are getting closer to 0.
Which means they are.
They should be,
But remember, they're getting closer to 0 from the bottom.
yeah.
They're getting bigger, right? The whole time.
Yeah.
But you said they increase and then decrease.
Okay, so the numbers are getting closer to 0. Can you go back to the other spot? Or
Yes, I can, but I need you to understand this part here, because this is that exact same thing that we had in that question on test 3
Oh yeah.
that everybody got wrong.
Yeah, so
No.
I thought I feel like I should have got it right on the test after the
Not
homework.
bad, but
What did you put for the answer on the test?
I put that a change of -3 is bigger than
Really
a
bad
change of
painting.
-1/3.
where'd you?
Oh, maybe you're talking about a different question than I am.
Yeah, I think so.
Oh yeah.
I'm talking about let's see, where is that test? I'm talking about this question, test 3, question 2. I'm talking about this question right here.
Yeah, I thought the question on the homework was similar to that.
It kind of is. It's got a numerator. It's got a denominator. It's kind of like that. Okay, I'm with you so far. But the biggest difference is, if you remember on the homework, the intervals were 100 to 200, 200 to 300. All of the intervals were the exact same size. Mm-hmm. And as you got farther along this way, you got bigger numbers, right?
Bigger numbers, but the change is greater. And I thought...
hold it. Say it again.
The number is bigger, but the amount of change is greater. And I thought that's how it was worded in the homework, too. So I feel like that should be right on the test.
Which one is the right answer for number 2?
It should be A, but the answer was C.
The correct answer is D. Yeah.
Yeah, because even in the review, like we had a similar question to that, and the review, the question was false.
Here's
what
what
you said yourself. It was a
no,
trick
you can't.
question.
Here's what you guys are trying to do. You're trying to make the question say, we care what happens to this. In this case, this is that stress function. We don't care about the stress function. We care about the slope of the stress function. And the slope of the stress function is always negative. The function is always decreasing, correct? But it's decreasing less as you go farther and farther this way. And this is the important part that I think you're missing, but I'm not positive because I don't know where you're thinking is. The stress is the average rate of change is getting bigger all the way along. It will never get bigger than 0. It will always be negative. This function is always decreasing. This function is always increasing, but it never crosses 0. Now I'm ready to go back to the question if you are.
Couldn't you say that the rate of change could be like a distance, and distance can't be negative? Like, you can't have a negative rate. So, like, -3 is a farther distance apart than what -1/3 is. So it's a bigger rate.
Okay, we'll talk about that in just a second. So on this question, you said red X. They said the correct answer was green star. I need to know why you think the stress first decreased and then it increased.
I put A on this because that's what the test question had. If we had a larger area, say 10, which was the thing on the test, 10 or 11, then...
I see what you're saying. Okay. Oh, where did the test go? Okay. I don't know that I can cure your thinking, but I know what you're thinking. Okay? Here's what you aren't disagreeing that 2 is more negative than 10. You're not disagreeing with that part.
No.
You're disagreeing with the fact that 10 to 11 and 10 to 10.5 to 11, that this slope is bigger than this slope. Is that what you're saying?
Yes.
Okay. Can I draw that part of the graph? So I'm going to draw the graph from the point 10 to the point 11, and I'm going to also have the point 10.5. Okay? So my graph, and I'm going to do it not to scale, just so that you can see. Okay, so I'm doing it so that it's a really big exponential curve. Okay?
All right.
Here is the value at 10. Here is the value at 11. Here is the value at 10.5. Okay? Here is the slope between 10 and 11. Here is the slope between 10.5 and 11. Okay? Would you agree they're both negative?
Yes.
Would you agree that if you're talking about negative, the largest value is the one that's closest to 0? Which one of these slopes is closest to 0?
Between 10 and a half and 11.
That's why that's the correct answer.
Okay. On the test we put 10 to 11, the homework I thought was saying the smaller numbers.
No, now let's look at what the homework is saying. Here's where the homework is different than what you're saying. If you look here at this table, here's the difference. Do you see that all of these are 100 apart?
Mm-hmm.
Okay? So they aren't making the intervals shorter. They're keeping the same intervals. As you get bigger and bigger and bigger and bigger, as the post gets bigger and bigger and bigger and bigger, the amount that the stress changes gets virtually nothing, right? It shrinks down to nothing. But it's always negative, which means it's always increasing.
Doesn't it say, though, that from 200 to 300 is a larger rate of change? For the answer?
We're in here.
Yes.
You got to show me where you're talking about.
Just the question that I got wrong right below it.
Okay, let's look what... Okay. They say, write a sentence that describes this column here of the table, the second column of the table, compared to the first column of the table.
Yeah. Okay. So as the area increases, the amount of change is getting closer to 0, which means that closer to 0 should be a greater increase since it's less negative. So I think A should be right, how I answered it there. Because the one below it says the area increases, the rate of change is decreasing. So it's changing by 0.007 between the bottom one and like 0.2 or whatever on the top.
As the area increases, the rate of change... Okay, and what are you saying the correct answer should be? Because I can't see that A is the correct answer. Because it doesn't go down and then back
I feel
up.
like A is what you're telling me the answer is. As the area is increasing, it means that your answers apart are getting closer together.
As the area increases, the rate of change... Give me one word. That's all I want to know, one word. Don't say it gets closer together. That's not one of the choices. Increases or decreases. Those are your two options. Now, looking at it, my first hunch right now, as I'm looking at it, my first hunch right now is that D is the correct answer. As the area increases... No, it's always decreases.
Yeah, and I guess I'm seeing it as the homework and the test do not agree. Like one is saying one thing and the other is saying another.
Because one is saying one thing, one is asking one thing about it, and the other thing is asking something else about it.
What are they asking differently then?
This is the test question. As you go farther this way, what happens to the graph of the slope?
It's of the slope is getting closer to zero or going up at a less and less rate.
But it's going up. Okay? That's where you get to the second part that the homework assignment is asking is comparing from here to here, to 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 from here to here, comparing each of these. What's the relationship between these as you go along?
It's going up less.
Change is decreasing, right? Or as you just said, it's getting less and less. What does it mean to get less and less? It means to decrease. Okay? It's a trick question. It's asking you something that in college algebra you aren't ready for, but that's what we do in trigonometry, in calculus. We do those rate of change problems all the time. And the beauty of the exponential function is that if the exponential function is like this, its rate of change is also an exponential function, negative. Page 323. Compound interest. Investment A requires that you deposit your money in for 1 year, then returns your money after 1 year with 10% add. B requires your money for 6 months, then returns your money after 6 months with 5% added. Which is a better deal? So it's just like that graph that we did here, which said the more often you compound, what happened? The more money you get. Let's look at the math that they ask us to do on the next page. So, if we compound $100, 10% the number of times per year. So, let's write down the formula for each one of these. The first one will be $100 times 1 plus 10% to the first. So, $100 times parentheses 1 plus, how would we write 10%? 0.1 to the first, and we get $110. Next one, 100 times 1 plus 10% over 2 to the second. Good. So 100 times parentheses 1 plus 0.1 divided by 2 to the second. And we get $110 and 25 cents. 100 times 1 plus 0.1 over monthly to the 12. So 100 times 1 plus 0.1 divided by 12. Oops, I have to start over again. Parentheses 1 plus 0.1 divided by 12. Close parentheses to the 12 is $110.47. 100 times 1 plus 0.1 over 365 to the 365. Eric, I'll let you get caught up because it looks like you're a little bit behind there. It's on the next page. Oh, you don't. The table is on the next page. There you go. Gavin, you caught up?
Yeah.
I'll let you get caught up. Manoni, you got to talk again.
Hello, hello, hello.
Thank you.
Hello, hello, hello. There you go.
It must be those trains over in Chippewa that are causing it to happen. I have to get to attendance here. Is that going to be okay with people?
I guess.
Oops. Okay, Nick, Michael,
Yep.
Merlina, nope, not today. Gavin, Janae, Felicia, Nicole, Eric, Phil,
Yeah.
Grant, Connor is here, Eric is here, Madeline's here, Jessica's here, Lauren is here, and Sam is here. Okay. So the next one will be 100 times 1 plus 0.1 over, and they just have it as a product, 365 times 24 to the 365 times 24. So 100 times parentheses 1 plus 0.1 divided by, and I'm just going to use parentheses in the denominator, 365 times 24, close parentheses, to the 365 times 24. So if you notice, that whole thing is in the exponent, and I get $110.51. So if you notice, it always increases, but the amount of increase gets smaller, right? Here, the increase is 25 cents, then we're down to 22 cents, then we're down to 4 cents. So as we compounded more and more, the amount that we got became less and less. Number 4 talks about that total after 1 year. Well, we've already done the math for that. If we get 100% interest, we had that on this table over here, right? If we compounded it yearly, we end up with 2. If we compounded every 6 months, we ended up with 2.25. If we compounded it monthly, we ended up with 2.61. If we compounded it daily, we ended up with 2.71. Hourly and secondly, it doesn't matter. It's still going to be about 2.71. So, number 5 talks about continuously compounded interest. The amount of money that you have in the bank after a certain amount of time is given by P times e to the rate times time. So in other words, the rate, went from being 1 plus this r, it went from being in this section here to suddenly being part of the exponent here. If you remember that function we just got done with, f of x equals x plus 1, this is where that number came from, x plus 1. G of x is a to the x. This number went from being down here, from being part of the base, to being part of the exponent. That's a significant change. The reason why it's so neat is it helps us realize some important things. What this is saying is, if we take this number here is always going to be, in this case, 0.1. Why? Because it's increasing by 10% per year. The other form we certainly could use, for example, if we wanted to know how long it took to double, we could take 2 to the t. Okay? That helped us. This is the doubling time. But this is what happens when you have a 10% interest time. Page 327. We've been talking about exponential growth. Way back when we were talking about foxes and rabbits, if you recall, or eagles, I guess it was, and Ebola, if you recall, we talked about exponential growth. What would eventually happen with Ebola if it had exponential growth? Eventually, everybody would have it, and everybody would be dead. Doesn't make sense because we know diseases don't ever kill everybody. What is the factor that happens to slow down that exponential growth at some point? I can think of a few. Natural immunity is one. There are some people that are immune to things, but the other thing is they don't come in contact with that particular organism. So you end up with logistic functions. Here is a logistic function. You have some base and you have some maximum value. So over the course of time, what happens is you go from this base, you may increase exponentially, but then you will unincrease exponentially until you reach that maximum goal. One of the logistic functions is population. Another logistic function is test questions. Okay. This is the probability of correct. What do you know is going to be the maximum probability that you can have on a question? 100%, right? And you could have 0% chance would be the minimum. You can't get less than minimum, than 0. Now, most of the test questions that I give you don't have 0 as the bottom.
Thank God.
What? Thank God. What do we do so that you have better than a 0% chance of getting the test question right?
Group test right now.
Top choice.
Multiple choice, right? So what's the minimum value since it's a multiple choice question? 25%, right? Now, as you get more and more people, you've got those that test poorly and those who test well. So those who test poorly maybe they aren't going to get lower than 25% chance of getting it right as a group. But at some point, that growth is going to increase like this, okay? A good test question will have a change like this. In other words, you can tell that a person is going to get the question right based on whether they're a good student or a bad student. Here is a bad test question. Why is that test question bad?
Not very many people did well on it.
And the reason that you did well on it had nothing to do with whether you knew the stuff or not. It had to do with some other factor that was going along. So that logistic growth was very, very slow. You think about it in connection with what they're talking about in this example with the penguins on the island. Okay, what's happening here? Well, the penguins are on the island, but over the course of several thousand years, they gradually increase. That's hardly exponential growth or logistic growth. It's almost linear, right? I mean, you have penguin chicks. You don't have penguin chicks. It's all the same. What they're talking about, though, is how do we find this logistic growth model? Well, in our notes, we need to capitalize on some parts of this equation that are very, very helpful. One of the things that you need to see is you have e to the RT in the numerator, and you have e to the RT in the denominator. In the denominator, you're subtracting 1 from it. In both cases, you're multiplying it by p sub 0, or in other words, the beginning population. In the numerator, you're multiplying it by k. In the denominator, you're adding k. So, if you multiply by a number versus if you add that number, what's going to happen? If this number is big, multiplying is going to make this a bigger number, right? If you just add it, it's going to not be as big. Everybody agree with that? Okay? So this is going to cause the function, as you go along, to grow. Why does the function quit growing quickly? It's because of this part right here. If you take e to the RT, notice t is getting big. That's the only thing that's changing. T is getting bigger and bigger and bigger and bigger. If you subtract 1 from it, that's going to, as it gets bigger and bigger and bigger, it's going to get bigger and bigger and bigger slower, right? That's what, so this part is causing the curve to slow down. This part is causing the curve to speed up. So the k, as k gets bigger, it causes this part, or the k is affecting this part of the function. The e to the RT is slowing down this part of the function. Actually, the k is more has to do with this part right here, just the middle part. So, how are we going to determine that function? Experiments with different values of k for the logistic function to see how you can fit the data that corresponds to the point t equals 10 years. So here we go. Next page. we're given this table. 0. At time 0, we have, I forgot to give the beginning part of the function. Population as a function of time equals. Okay. Here's our table. We want to know, how do we get it so that 10 years we get close to that number? Well, let's fill in the stuff that we know. In our formula, this is crucial. We know this number is 501. P sub 0 means the population at the beginning, 501 people. What is the value of K? Well, K influences this part of the graph, but it actually is the carrying capacity, or the maximum number of penguins that you can have on the island. So the easiest way to do this would be to take the rate times the time. And let's say the time is really big, like let's say 1,000,000. So if we took E to the million, 1, 2, 3, 4, 5, 6. Oops, it won't let us go to the million. Quit. What will it let us go to? E to the 1,000? Will it let us do that? Nope. Will it let us do E to the 100? There we go. E to the 100 is 2.68 or 69 times 10 to the negative 43. If we take that value and subtract 1, answer minus 1. Why does it still say 2.68 times 10 to the 43rd? Oh, that's to the positive 43rd. It's positive. I didn't realize that. Sorry. It's positive 43rd. So in other words, that won't affect the time will not affect the population, only the initial value. I don't know. They don't give us the initial growth rate in the book here. We must have to get that from the preview. Let's go to the preview and get that value. Chapter 25, preview. It says 17% per year. So this value will be e to the 0.17t. This value down here will be e to the 0.17t minus 1. So on our graph, I think that's the way they want us to do it, is using the graph, 25a, logistic growth. So here's our function, and they give us those values. They say, well, what is a good approximation for k? If you notice here, it says k is about 9,070. So 9,070, but that's if the growth rate is 16%. They want us to have the growth rate be 17%. So it'll be around 7 or 9,000. So we'll put in 9,000 in the numerator and 9,000 plus 501 e to the 0.17t in the denominator. If a scientist wanted to predict the penguin population at 25 and 30 years, what would the logistic model predict? Well, we would just change this number to 20 and then change it to 30 and see what we get for the times. Or if you have it graphed in Desmos, you'd just go out here 20 years. It looks like we would have a population of about 5,400. 25 years, we'd be at about 7,000. And 30 years, we would be at about 8,000. Page 329. We've been dealing with exponential functions, and in every case, the exponential functions we've been dealing with so far, we've known where this initial value is, a. If you look at the graph on page 330, you don't know where it's going to backtrack to. So if you take these high points and you back upwards, where does it look like you're going to cross the y-axis? At about 3, something like that. We're going to figure out, in this case, if we start here, 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 and here, where do we cross the y-axis? What is the value at that point? So we're going to learn how to make an exponential model. Here's how you do it. Step 1. For a function, as a function of time, for an exponential, you have a times b to the t over your interval, whatever that interval is. This b is the ratio of the new to the old. Let's go through our table here on page 329 and find what the ratio is between the new and the old. So let's 0.3, 1.55, 2.8, 4.05, 2.22, 0.622, 0.174, 0.048. So the first one that we want to do is 0.622 divided by 2.22. 0.622 divided by 2.22. We get 0.28. Next one. 0.174 divided by 0.622. We get 0.28. 0.048 divided by 0.174, we get 0.28. So we're going to take 0.28 to the t. But now, how big is the interval over here? I should have made this in red. Okay, how big is this interval? How big is this interval? How big is this interval? How far is it from 0.3 to 1.55? How far is it from 1.55 to 2.8? How far is it from 2.8 to 4.05? So the only value we're missing is, where does this graph cross the y-axis? If we were talking about linear functions, do you remember? I'll draw a picture. That might help. Here, for a linear function, we had these 2 points right here. How did we determine where we crossed the y-axis? Well, we knew the slope, right? And then we just substituted in one of our points. The y value here compared to the x value here. So we just put the y in here and the x in here, and that helped us determine what the b value was. The same thing is going to be true here if we talk about exponential growth. Here we know the ratio, we know the time interval, we know these two values here. All we have to do is keep on backtracking till we get to this value a here. So let's substitute that into our formula. One of the points that we have. Purple. Let's take this very first point. It tells us that our answer, 2.22, is equal to our a value, which we're looking for, times 0.28 to the 0.3 over 1.25. How do we get the a all alone? How do we get the a all alone? Divide both sides by 0.28 to the 0.3 over 1.25. 2.22 divided by 0.28 to the 0.3 divided by 1.25 is, our a value is 3.01. Does it look like, if you backtrack to the y-axis, it goes through 3.01? Keep on going backwards. Looks like it crosses right at about 3. We will start there on Monday. We got a little bit ahead. It'll be aggressive to get done with all 4 of those assignments next week, but we should be able to get close.
That's it for what you did. That's good.
Oh, I don't need it. Are you okay? Are you going to be okay? Okay. Okay. Janae, Madeline, right? You're seeing me after class? Okay. That's boogie boogie. See you, Sam.
Yeah,